Okay, as I mentioned in the last video, I want to just do a couple of homework problems from section 16.2, or sorry, 6.2. If you haven't already done the homework, go away, do the homework, then come back and check in. So I'm going to be looking at question number 16 and 17 in this video and the next video. Okay, so give those a shot first. If you feel totally comfortable with them, 16 is an even number, so I've got a solution posted online. 17, you can check your answer in the back of the book. If you feel really comfortable with them, don't decide not to watch the videos, that's fine. If you struggle with them, even if you get the right answer, I'd recommend watching the video. And if you struggle and don't get the right answer, I definitely recommend this. But I do recommend that you work on the problem first. This is a tough problem, okay? And so if you struggle with it and you don't see it, and you need some help, that's totally fine. Watch the video, but you'll get more out of it if you've struggled with it first. Okay, so just to clarify, this is formula 14, which we will be using in the problem, and this is problem 16, which is what we will be doing. So problem 16 deals with a periodic function. So f of t is periodic with period t. Classic examples are our trig functions. Okay, what it means to be periodic is that if you plug in any number plus the period, you just get out the same value as if you plugged in that number. Okay. All right, so we're asked to show that the Laplace transform of such a function is just a multiple of this integral. Now notice that the integrand is the same thing that I would get for the Laplace transform, but instead of going from 0 to infinity, we're just integrating over one period from 0 to t. Okay, and then we get this multiple of that. Okay, kind of a neat thing. Let's check it out. Okay, so hopefully that answer will reappear after some hard work. But I'm going to just use the definition. This is the integral from 0 to infinity of f of t times e to the negative st dt. And I'm just going to break that up and say that's the integral from 0 to t of f of t e to the negative st dt plus the integral from t to infinity of f of t times e to the negative st dt. Okay. So I'm going to just focus right now on this piece and try to sort of rewrite it. Okay, so just looking at that piece, the integral from capital T to infinity of f of t times e to the negative st dt. Okay. I'm going to observe that we're integrating from t to infinity. But if I were to just define this function to be 0, from 0 to t, then I could extend this to integrate from 0 to infinity. I'm hoping to make this look ultimately like a Laplace transform of something. I've got pretty much a good integrand, I've got a good upper limit of integration, I want to have that being 0. So what I'm going to do is I'm going to replace f of t with mu sub t of t times f of t e to the negative st dt. Now why can I do that? Well, let's take a look at this. Mu sub t of t times f of t would be defined piecewise. It would be 0 if t was less than t, but it would be 1 times f of t, so it would just be f of t if t was bigger than or equal to capital T. So I can integrate this from, the whole point of that was so that I could change that lower limit of integration to being 0. Because now when I'm integrating from 0 to capital T, I'm just integrating 0, so it's not affecting the value of things, okay? And then when I'm integrating from capital T on, that's what I was trying to get. Okay, kind of nice. Now, this is looking like a Laplace transform, but it's a Laplace transform of this. And that doesn't quite match my formula here. If I'm turning this on at capital T, I'd really like to have this be translated by a distance of capital T. Okay. So what I'd really like to have there instead is f of little t minus t. So are they the same? Yes, because that's the period. This is a periodic function. Now, as I stated it here, if you have a value of t and you add a period to it, it doesn't change the value of the function. But the same thing works if you subtract a period. Think about sine. If you're at a high point on sine and you add 2 pi, you're at another high point. If you're at a high point for sine and you subtract 2 pi, you're at another high point. I could also see, if I plug in this for t, I could say this is, well, if I look at f of t minus t plus t would equal, obviously, f of t. But according to this rule, that's also equal to f of what I started with, which is t minus t. Okay. So I can actually replace this little t with t minus the period t because it's a periodic function. So I can say this is the integral from 0 to infinity of mu sub t of t times f of t minus big T e to the negative st dt. But now that is the Laplace transform of mu sub t of little t times f of t minus big T. Because it's that function times e to the negative st integrated from 0 to infinity. That's the definition of the Laplace transform. Okay. But now I can use rule number 14, which says that this Laplace transform, actually let's work this out. So we were working with just this piece. Okay. So essentially, let me just rewrite all of this. We have the Laplace transform of f was equal to this integral from 0 to capital T of f of t times e to the negative st dt plus this piece, which we just spent some time saying was the Laplace transform of the Heaviside function at capital T times f of t minus capital T. But now I can use formula 14 here. So I can say the Laplace transform of f is the integral from 0 to t of f of t times e to the negative st dt plus, here we're going to get e to the negative capital T times s times the Laplace transform of f. Yes. Sorry, I was I was having a brain fart for a moment. I think I've stopped doing that now. Okay, notice this is what I'm trying to solve for, and it shows up twice in my equation, once on the left side and once on the right. I'm just going to subtract these pieces over. So if I do that, I get the Laplace transform of f minus e to the negative ts times the Laplace transform of f. All of that's equal to the integral from 0 to capital T of little f of t e to the negative st dt. But now I can factor out that Laplace transform. So the Laplace transform of f is being multiplied here by 1 minus e to the negative ts, and that's equal to the integral from 0 to capital T f of t e to the negative st dt. Now I can solve for this, so the Laplace transform of f is going to be 1 over 1 minus e to the negative ts times the integral from 0 to t of f of t e to the negative st dt. So, kind of a neat trick for periodic functions, and just a little bit of an interesting way of getting there by sort of rewriting things and taking advantage of the fact that this function was periodic.